elements. And for instance, p sub k minus 1 would look like this one. Right? This is p sub k minus 1, and p sub k plus 1 would look like this one. Right? So there are many functions defined in the interval. And assume that you are solving a problem from somewhere here x0, right, up to, for convenience I will say, xn. Then we need finite elements like this, right? It is p sub 0, and a finite element like this, p sub n. Right? P sub n. So if I write it, P sub 0 look like this. P sub n look like this. Right? P sub 0 and n. And then something in between, right? So these are finite elements. And how many of these should exist here? Should be capital M plus 1 functions, right? There are total capital M plus 1 functions. Then the idea is this one. To solve a differential equation, instead of solving it directly, instead of solving this one, we solve a weak form coming from the integral. In other words, we do the integral from, for instance, this endpoint x0 to xn of function, right? This function multiplied by p sub k of x dx, and then because this is 0, the integral should be 0 too. So this direction is always correct, but the other direction is not necessarily correct. So this is the reason why it's called weak form. So this direction is always correct. This direction isn't necessarily correct. So we can create this kind of equality for each k. So k could be 0, k could be 1, k could be 2, k could be n, x sub n. So for each, we can do this kind of integration. I will do the integration of y, second derivative of x part, and then later I will handle this thing. So let's do this integration. Then by integration by parts, last time I showed this thing. Because of integration by parts, right? I applied integration by parts, and then minus. And as you can see, we don't know the value of y prime. It doesn't have any information of y prime of x. It doesn't have any information. But we have some information about p sub k at many nodes, right? P sub k is non-zero only at xk, right? At other nodes, it is 0. So this will vanish in most cases except the case when k is 0 or k is n. So these are two possible cases. So we don't apply this to p sub 0 or p sub n, right? Do you follow me? So we don't apply this integration by parts to p sub 0 or p sub n because we have p sub 0 of x0 equal to 1. Then we don't know this value. Then we cannot calculate this value. Or we don't know the value of p sub n of x sub n. We don't know this. We know this value, but we don't know what the value of y prime of x is. So we don't use this formula for these two cases. Then how do we compensate? we use boundary condition. So for these points, I will go to the next column. For these points, we use boundary conditions given by the problem, right? We are solving boundary value problems. We are using boundary values given by the problem. These are the stuff that I covered last time, and if you have any question up to this, ask me. Then let's resume. Last time I wanted to solve the problem, and do you have the problem sets? If you don't, then I will return back to the notes. So if you have the problem set, please let me know. Why second derivative? What problem did we try to solve last time? The same one? Exactly the same? Great, I have good memory then. Then we wanted to solve this problem with y of 0 is 1. And in my opinion, I didn't use 1. I used some other number. 6. So this is the one we want to solve, right? So let's try to solve it. Then we should create the functions like these. This is 0. This is 1. Was it 0? Was this 0? Right? So this is the case, right? So this is the phi 0 function. And then phi1 function, phi2 function, phi3 function, and then this is phi4 function. So the solution is given by this. By boundary condition, 1 times phi0, and then c1 times phi1, c2 times phi2, c3 times phi3, and then 6 times phi4. Up to this point we covered. We know what y is. Then let's plug this in. If we plug this into this relation, then y first derivative is replaced by this derivative, and then this replaced by something, and so on, right? We replace this by this derivative. Let's do it. But before going any further, let's write the full description. I wrote the weak form of the differential equation for k. If you follow me, I rewrote the differential equation after attaching these things, and it's time to replace this by the integration parts result. By integration parts, by parts, as you can see, this term, this integral becomes this one. And then as you can see, if you plug in these numbers, because k is not 0 or n, this term becomes always 0, right? So this whole term vanishes, right? This whole term vanishes, and the only surviving term is here. So let's write the result. Because of this reason, it is written this way. Now x0 is 0, and xn is 4. 0 to 4. Or we can write these things in one integral. So let's write it one integral from 0 to 4. And then I move this to the right hand side then. Y prime p sub k prime plus 4 times y p of p sub k dx equals 0. Up to this point we covered last time. And then if you have any questions up to this point, ask me. Okay, I will show you the actual calculation of these things using this y replacement. So what I will do today is this one. I will replace y or y primed by these things, right? So y is replaced by these things. Then, essentially, it's good to write this in some notation. So I will use the sum notation. Sum piece of k. K is used here, so I will use different index. So instead of using k, I will use, for instance, j. Right? C sub j, and then p is coefficient c sub j, right? And then c sub 1, and c sub 0 is 1, c sub 4 is 6. So I will use this sum notation. Then from y, we can get this result. From 0 to 4, y prime is sum p sub j, p j prime, right? I differentiated this thing and then multiply by p sub k prime plus four y is replaced by this one, and then multiply by p sub k, and then dx equals 0. So a simple replacement, right? Simple. Y prime is replaced by this one, y is replaced by this one. Then we can switch the sum and integral. In other words, this sigma can come out, and this sigma can come out of this one. Then what you will get is this one. Just straightforward calculation, right? I just switch integral and sum. So here, all these are numbers. All of these are numbers. All of these are numbers. And we will calculate these numbers. And with these numbers, we can create a system. Any questions? Then let's do it. So take a look. P generally, J and Pk are in many places zeros. Right? In many places these are zeros. Only when they are adjacent or the same, right? So adjacent or the same, at least they are somehow connected, they may not vanish, right? So this pair does not vanish. Only if the difference of these two is 0 or 1, right? In other words, they are adjacent or they are the same. If they are 2 units away, what happens is this one. It may be here, right? And the other may be here. Then if you multiply this function, what happens? Multiply these two functions, then this becomes 0 in this area, and then the other becomes 0 in this area, right? So always if you multiply two functions, they become 0, right? So the result becomes 0. So if you multiply two functions, it becomes 0. So only they are adjacent, or they are the same, it does not vanish. This tail does not vanish. Product y, derivative of product also. So these two do not vanish if they are close enough. So we don't have to consider all possible pairs of j and k. You only need to consider about the cases when they are equal or one apart. Do you follow me? Then let's do it. First of all, for convenience, let's divide four possible cases. P sub, generally I will use another letter such as m, P sub m, and then P sub m multiplied. Right? This can appear from 0 to 4. Do you follow me? What else is possible? P sub m, and then P sub m plus 1, or the other way, right? P sub m plus 1, P sub m. This can appear. What else? Derivative, right? Derivative. P sub m derivative, P sub m derivative can appear. Or P sub m derivative, and then P sub m plus 1 derivative. So generally, these are possible cases, right? M may vary from 0 to 4. These are all surviving terms, or others cannot survive. So even though there are many possible multiples like these, many terms disappear because at most places these functions are zeros, right? At most places these functions are zeros. So the only terms that survive are terms like these. If you find other terms, then just ask me. Then let's calculate the integral of P sub m and P sub m. And take a look. We are multiplying this function by itself. Right? This function by itself. Then, for instance, if you consider the function at xm, right, at xm, then xm minus 1 position, xm plus 1 position looks like this, and then this function can be calculated. It is like middle school geometry. Of course, we have 2 points, then can you find the equation of this line? I will go to the next. We are handling phi sub m here, phi sub m, and then xm, and then xm minus 1, xm plus 1. So generally, assume that this distance is h, right? This distance is h. Then, this point is like this. xm minus h is the x coordinate. And then 0 is the y coordinate. And this point is xm, and then 1. Do you follow me? At nodes, at surrounding node 0, at this node, xm node, it is 1, right? The height is 0 and 1. And then node. Then how can you find the equation of the line passing through these 2 points? y minus y1 equals y2 minus y1 over x2 minus x1, and then x minus x1. So this is the formula that you can use. And if we simplify, y equals 1 over h, x minus xm plus 1. So please check it. When x is equal to xm, what happens? When x is equal to xm, y is what? 1. When x is equal to xm minus, when x is equal to xm minus 1, then what happens? This is minus h, so plus 0, right? Minus h over h is 1, negative 1, and then plus 1, 0. So this is correct. And the other way is possible, right? You can calculate the other function, and the other function has only this difference. Has only difference. This becomes plus, right? This becomes plus. Because of this plus, now take a look. This becomes so the other function. This part is calculated here. This part is calculated here. The other part can be calculated. The other part is okay. Oh, I might make a mistake. Sorry for the mistake. There is no mistake. Oh, yeah. These are minus. So the other part you're changing is this is negative, right? This is negative because this is subtraction of x and then it's negative. Thank you. This part. I got very crazy about it. And then because of this negative sign, h becomes plus. So this is plus. I made a mistake here because if you use plus here, then it's minus here, and then this minus affects this one, and then so if you check it, you get the result. So let's check it. If it is xm, then what happens? If xm is replaced, what happens? Yeah, 0. This is 0 for this one, right? So it is xm plus 1. What happens if it is xm plus 1? Then xm plus 1 minus xm is h, right? H over negative h is minus 1 plus 1 is 0. So this function is correct. Then what is Pm squared? Pm squared is what? Pm multiplied by Pm. Pm squared is what? Multiplying this, right? H x minus m plus 1 squared, right? And then minus h x minus m plus 1 squared, right? These are two functions. So we are integrating these two functions from, we are integrating these functions from 0 to 4. Do you follow me? Just simple integral is done. Simple integration is done. Then let's break up the interval. So from xm minus 1 to xm, we should use this function. And from xm to the next one, we should use the other function. And then at other points, all 0, right? At other points, all 0. So we multiply Pm and Pm and Pm. So we got this. So please check whether you completely understand everything up to this point or not. Let's do the integration. For convenience, I will use symmetry, right? These two are symmetric, I will just calculate this half, right? I will calculate this half, then I will double it. So I will use just, I will go to the next column and then write the second half. You follow me? I'm using symmetry to find this thing. And we are now ready to handle this problem. And for convenience, I will use integration by substitution. So let t be equal to x minus xm. Then dt equals dx, and this is the number. And the boundary changes. X equal to xm becomes t equal to what? X is equal to xm means t equals what? X equals xm gives us t equals what? 0. And x equals xm plus 1. Why xm plus 1 is xm plus h, right? Xm plus h distance away. Then t equals what? When x is equal to x sub m plus h, then t is equal to what? H. So we are now rewriting the integral, and it's 2, 0 to h, minus 1 h, and then t plus 1 squared dt. Then it's just calculus problem, right? This is a calculus problem. 0 to h minus 1 over h t squared plus 2t over h plus 1, and then integral dt. And then if you integrate this thing, then 2. If you integrate this thing, 1 over h squared with 3 t cubed, and then this integration gives us t squared over h, and then this integration gives us t from 0 to h. Then now replace t by h, and then t by 0. If you replace, then what happens is this one. H cubed over 3h squared minus h squared over h plus h. The total is 2 times what? 3h is the common denominator, and 3 is the common denominator. And then also h can be extracted too. H is extracted too. Then the remaining part is 1 minus 3 and then plus 3. Oh, you could cancel. So this can be done. Then 2/3 h, right? So depending on the distance h, we may get different numbers. But if h is, for instance, 1, then the integral involved in this is calculated. So you should do calculation of these 4 terms. I did one case, right? I did one case. Any questions? Then, because of the same reason, but I will write the result. I will write the result first. Because of this reason, Pm multiplied together from 0 to 4, dx gives us 2/3 h. Then let's do other cases. Without loss of generality, I will do these things at convenient settings. So Pm plus 1 dx will be done soon. And it looks like this. This function looks like this. And then this function looks like this. And then the only area that the function, the product does not vanish is this area. Within this area, the product does not vanish. For instance, if we consider this point, then because this 0, this multiplied by this one is still 0, right? If you pick this point, then this multiplied by this becomes 0. So the only area that the product, right, the product does not vanishes in this area. So we need to do integral over this area. So do the integration. Integral from 0 to 4, then it's like this. 0 to h, right? So we will consider 0 to h. Do you follow me? 0 to h. After translation, right? So we are, instead of using x-axis, we are using t-axis, right? And t-axis is from 0 to h. 0 to h. And this function is 1 over h times t. Do you follow me? This function is 1 over h times t. And then the other function is 1 over h and then 1 minus t. I translate it the same way as this one, right? Instead of considering xm, I consider t. Then instead of considering xm to xm plus 1, we are considering 0 to h. Do you follow me? So instead of considering xm to xm plus 1, we are considering 0 to h with this translation. I feel something strange here. I might miss something, like 1 here, right? I think 1 is missing. So I should have written the same in the same pattern, right? Minus here, plus and minus. I should have written down in this kind of pattern, right? So when t is equal to 0, still wrong. What is wrong with this? Sorry for the mistake. What is wrong here? Let's calculate. Let's find the equation of this line. It should not be difficult, right? It should not be difficult. Y equals 1 minus 1 over h is the slope, right? And then reduced calculation is not coming. I will just slowly. That's middle school calculation. Middle school calculation. I will do this. We have points like 0 and 1, and then h and 0, right? So we should have a line passing through these 2 points. I'm having a hard time finding this. Let's do it. Y minus y0 equals y2 minus y1 over x2 minus x0, and then x minus 0. So this is the one, and minus 1 over h, and then y is minus 1 over h times x plus 1. So this is my mistake. Oh, I fixed x t instead of that. I replace x by t. So this is my mistake. Then let me check. If t is equal to 0, then y is 1. If t is equal to h, then 0. Great. So this part was my mistake. I should have removed this part. I somehow did this inside my head, and that was wrong. So this is the equation passing through 0, 1, and h, 0. Right? We are handling 2 functions. we are handling this function and the other function. This function is not difficult to find. The slope is 1 over h, and then starting at 0, so it is just this one. The other function is not difficult either, but I had a hard time, and now I corrected. This is the function. So we need to do this integral for adjacent functions. So one is going this way, the other is going the other way, and we should do the integral. And let's do the integration. After removing this embarrassing middle school part, let's do this thing. Then, first of all, I will simplify 1 over h squared with minus sine t plus 1 over h t. Should we integrate it? And if we integrate these things, then minus t squared. Thank you. h squared, and then cubed, right? Because of this t cubed. And similarly, 1 over 2h, and then t squared, and then from 0 to h. This is the simple calculation. And afterwards, what happens? It is, the common factor is 1 over h, then minus 1/3, and 1, sorry for the mistake, it is h is the common factor. And this is 1 over 2. So 1, right, 1/6. This is that. So we should calculate 4 possible cases, but now 2 cases are done. So we have 2 remaining cases. Derivatives are easier. Take a look. Look at this function. Then around this interval, what is the derivative? Derivative is a slope, right? Derivative is a slope. And at other points, so the derivative is a slope, so t primed around this area, right? Something around this area equals the slope, right? 1 over h. 1 over h is slope. The other way is also easy, right? The other slope around the other area is minus 1 over, either 1 over h or 1 over. So let's write down those things systematically. So let's do this thing. 0 to 4 p sub m primed p sub m primed dx. And as you can see, it only survives at xm, right? This only survives at xm. So from xm minus 1 to xm, right? In this direction, it has slope 1 over h, right? And then this has slope 1 over h. And the next part, xm to at the next point, it has the slope minus 1 over h, and then minus 1 over h. So as you can see, at other points, 0, right? At other points, 0. So just constantly integrate it, right? So this gives us 1 over h squared multiplied by x. Multiplied by x. And the x running from xm minus 1 to xm. And this part is 1 over h squared multiplied by x. X running from m to xm plus 1. Then by calculation, xm minus 1, and 1 over h squared, xm plus 1 minus xm. And as you know, the distance between each node is h, right? This distance is h, this distance is h. So it is 1 over h squared multiplied by h h squared multiplied by h, then 2 over h. The only thing remaining is when we have crossing case. The prime. Now without prime we did with prime, with derivatives. Let's do it. Then, as you can see, when you have this kind of case, we have surviving terms. At other areas, we don't have surviving terms. Why? Because at other areas, as you can see, the function is 0, right? The derivative is 0. So, for instance, if we consider the other part here and then this part and multiply the derivatives of this is 0, 0. The only part that we should take care of is xm through xm plus 1, right? xm through xm plus 1. So we should do the integral of these things from 0 to 4, p sub m prime, p sub m plus 1 prime. These are the only cases we should take care of. You follow me? If we have 2 apart, then all terms vanish, 0, 0. I will just write. Right? This looks like this. This looks like this. And then this vanishes here, right? This function vanishes here. So no matter what is here, multiplication of these two vanishes, and this function vanishes. Even in slopes, right? Even in slope, the slope here is 0. No matter what slope is given, this part vanishes. So the only part surviving is the part here. The only part surviving is the part here. Right? So this area is the only part that you should consider. So the integral is reduced to the integral from xm to xm plus 1. Then as you can see, this function has slope 1 over h. The other function has slope minus 1 over h. This is it, right? And by the same reasoning, we get this result. Minus 1 over h squared multiplied by x from xm to xm plus 1. And this difference is h, so minus 1 over h is h. So we calculate all the necessary terms. And we will return back to the equations and then replace these kind of terms by just simple result. That's what we do. I will pause and you may write everything up to this point and ask. Let's do it. Then EJ, and then integral EJ prime, EK prime from 0 to 4 dx plus from 0 to 4 E J E K. Then only term that survives is this: j equal to k minus 1, k or k plus 1. Can other terms survive? In this combination, k is fixed, right? K is the function that we fixed. For the fixed k, j varies, right? J varies. But the only term that survives, the only terms that survive are these terms, right? J equal to this or this, right? All close to K. Because of this region, I can write it this way. C K minus 1, right? C K minus 1, 0 to 4, C K minus 1 prime, C K prime dx. And then 0 to 4, C K minus 1, C K dx. Right? So this term survives. And the next term, CK term survives. CK term survives. And 0 to 4, CK minus 1. Okay. And then C prime dx, in fact square, right? Square terms. Finally, K plus 1, as you can see, it will become a matrix with tri-diagonal entries, right? Tri-diagonal entries. From 0 to 4, K plus 1 find Ck dx plus 0 to 4, Ck plus 1, Ck dx. So all other terms vanish, right? In the sum with J, all other terms vanish but these. And it's time to replace this by the result. So I do not remember the result. What is this result? This result is what? What is this result? Or H outside? So I will come back to the calculation that I did. And then plus CK, and then in this case it is 2 over H. And what was this result? Was it this H over 6 right here? Because I cannot see the result. I'm in trouble. H over 6? Here, H over 6? Here, 2/3 H. Finally, this part is symmetric, right? This part is symmetric. This part is symmetric like the one. Right? So we could create this kind of tri-diagonal system. And in fact, some of you already know how to handle tri-diagonal matrix fast. Right? In numerical analysis, I mentioned it. But here you don't have to know, just solve this diagonal system because K varies from 1 to n minus 1. Right? K varies from 1 to n minus 1. In addition, we know what C0, Cn is. Right? We know what C0 is and what Cn is. Right? So we know everything by solving this. So let's complete this up. Unless you have questions. And I will solve the problem. Please remember this and let me know when we turn to the next page. generally, we can have this relation, ck minus 1 multiplied by minus 1 over h plus h over 6 plus ck multiplied by 2 over h, and then 2/3 h, and then finally ck plus 1, and then symmetric image minus 1 over h, and then 6h over 6, 0, right? So we create a system having these terms. So let's create a system really. And before doing it, let's replace h by 1. So let's return back to our problem. Our problem had line from 0 to 4, 0 to 3, 0 to 4, 4, and then 2 here, 1 here, 3 here, and then we have the functions around here. Then h is 1. Right? So I re-simplify this thing. If h is equal to 1, then ck minus 1, and then 1, 1 gives us what? 5, 6, right? 5, 6. And then this gives us what? What is the result? 8/3, right? 8/3. And this gives us what? 5, 6. If h is equal to 1, we get this system. So let's do it. When k is equal to 1, when k is equal to 1, what happens is this one. When k is equal to 1, C0, 5, 6 plus C1, 8/3 plus C2, 5/3, 5, 6 equals 0. And we know what C0 is, right? You know what C0 is. C0 is boundary, and it is 1, right? You know this stuff. But I'm writing down all the equalities slowly so that you can later return back to the idea part. So, sorry. And the next one is C1, negative 5, 6, and then C2, 8/3, then C3, negative 5, 6, right? And then finally, C2, minus 5, 6, and then C3, 8/3, and then C4, minus 5, 6. Right? So by solving this system, we may be able to find the C0, C1, C2, C3, C4, right? In fact, C0 and C4 are already known. So by solving this system, we solve the problem. And in fact, you can make these things simpler. But let's try to create a system. What is C0? C0 is what? 1. What is C4? 6, right? All these are given by the boundary conditions, right? Given by the problems, right? This is given by the problem, this is given. Then, as you can see, you can create this kind of system. C1 times 8/3 plus C2 times minus 5, 6 equals this number, 5, 6. And the middle one, C1 minus 5, 6, C2, 8/3 plus C3 minus 5, 6 equals 0. And finally this one, C2, negative 5, 6, C3, a6, a third equals 6 times this one, 5, right? So we wrote this. So if we solve this system for C1, C2, C3, then we can determine the coefficients in front of basis functions. That means we solve the problem. Let's solve it. So I will write down one more line before going any further, so that later you can systematically handle the problem. No matter how many basis functions are required, you will be able to handle these things. Generally, boundary function, right? Boundary values can be provided with this adjustment. So instead of saying just boundary value, I will write the adjusted value. Right? Boundary condition combined with this kind of number can be written here. So 5, 6, 5, 6 here, and then 5. So I will solve this system. Of course, Maple will solve this system. If you find any mistake, please let me know. I want to write it in verbatim. Or we can omit this thing. So these are the things. So about C1 is 0.23. So let's write it. Oh, sorry. You found a mistake. Thank you. That's very much improvement. So let's recheck everything is correct right now. So in my opinion, everything looks fine. But values are not very beautiful. So C1 is 2.14. Please remember these numbers. Oh, I see, yeah. C1 is 0.57, 0.578, right? Or C1 is 0.58, right? I will cut it there. And then C2 is 0.85. C3 is 2.14. So do you follow me? I solved the problem using finite element method. Yes? That kind of case is Neumann problem in general case, but we do not want to go into varying boundary cases here. We want to go into just this kind of boundary in this situation, but it's possible to handle the combination boundary problems. we have y prime, then we can solve the problem using initial boundary value problem. RK4, we can solve it. In other words, first term point is given, and the derivative is given. Then, by using 2, we can use RK4. That's the reason why we consider just boundary. You follow me? So initial condition, and then another condition gives us boundary. But if this becomes derivative, then it becomes an initial value problem. Yes. Oh, I see. Yeah, the same thing, the same. In other words, we just add y prime the term inside. I will show you, yeah. So, I see. Right after this, I will show that kind of case, general case. So, we will have the result like this. We said y equals C0, P0, C1 up to C4, P4, right? So this is what we initially guessed, and then we found all C's, right? So y equals C0, that is 1 times P0, and then 0.58 P1, and then 0.85 P2, and then C3, 2.14 P3, and then C4. So assume that you programmed these basis functions already. Then after solving this linear system, you just plug in the values, like say alpha, right? By alpha values, you can find the solution function, right? So this is what we do. So after this, I will consider general case, as you mentioned, right? Assume that we have y prime the term there. I compute between y prime in the initial condition and y prime in the differential equation set. Any questions? Then roughly, this is the situation. If we sketch it, because it's one-dimensional, all the functions are straight lines, right? So we know at least at 0. At 0, it is 1. Right? At 0, it is 1. At 1, it is 0.58, right? At 0.58. At 2, it is 0.85, right? 0.85. And at 3, it is 2.14, right? And at 4, it is already known 6, right? At 4, it is 6. So if we connect them, we can find the solution like this. In fact, my graph is not reliable, but at least giving you the idea. So we have found the solution. What is the difference between this one and the linear spline? What is the difference? Linear spline has only point information. We program something to fill these, right? To fill these by lines or curves. But here, it's not. All these are already defined in basis functions. Just by linear combination, we got this graph. That's it. So I completely explained the idea of FEM with lines. But before going into your question, we will consider other ideas. Why do we use just this kind of sharp, straight lines? What about like smooth lines? What if we use these things? Then, as you can see, we break up the interval into 4 nodes, right? Four sub-intervals, right? 4 sub-intervals. Then, in the past, we only considered about the product of these things for adjacent terms. But now, if we use this kind of function, we should worry about all these sub-intervals, right? In other words, if we have slight match, if we have very slight match here, then we cannot vanish them. So we should calculate all of those cases if you use these functions. So this is the difficulty. If if you use splines, we encounter this difficulty. Plus the derivative condition, right, cannot easily vanish, right? Cannot easily vanish. Because if you use this thing, we only exclude the end 2 points, right? The boundary points, right? But now, if we use splines, we cannot easily remove these things, some of these survive, right? Even, for instance, look at this. In the past, only thing that we dumped was this one, right? This one was dumped. And after this, we could have 0 here, right? We could have 0 here. But if you use these things, then we cannot dump this kind of function. We cannot dump this kind of function. And then we cannot dump this kind of function. The only function that we can dump is the function like this. As you can see, among 4 functions, only this can be dumped. So we should calculate all the values of these. So it's way over top, right? It's way tougher. So we try to use just linear spline instead of real splines. Then now let's return back to general differential equation. As you mentioned, assume that you have general differential equation like this one. Assume that you have these things. Right? Assume that you have these things. Then we do the same thing. We apply pk here, right? Pk here. And this term, and then this term, I handled similarly, right? The only thing remaining is this term, right? The only thing remaining is this term. And as you mentioned, when you have this term, then a times p prime pk can be done by integration by parts. By integration by parts, I will even remove a, right? Just consider this thing. Then y pk from, right, from xm plus 1, I mean boundary, sorry, x0 to xn. X0 to xn, right? Capital N. And minus y times p prime k from x0, xn. And then same thing applies here, right? Same thing applies. Because this becomes 0 for almost all points. We can vanish this thing and then we consider this thing. So we can combine this and this together in the formula. Then, in this kind of case, you need to find the terms like this. In fact, your concern is completely legitimate, right? The equations are not that simple, right? Equations can be very general. Then we need to calculate this. Why? Because this replacement, this portion has y piece of k prime combination, right? So y can be, this y can be this kind of term, or this kind of term, or this kind, right? So depending on the situation, we find adjacent term. If you don't follow me, ask me, then I will show you full detail. Am I too fast? Or you completely understand that? Yes. Uh-huh. You are right. You are completely right. Yeah, I missed 4. Yeah, you are right. So in my calculation, I somehow only calculated this part. I made a mistake there. I only calculated this part, right? I didn't calculate the other part, so sorry for the mistake. So next time, I will return back, because I only calculate this part equal to 0, not the combination equal. You're right. So, yeah, I made a mistake. Yeah, the only matter might be 4, right? 4 is not attached there, right? That might be the, right, so that might be the problem. So, yeah, so as you can see, somehow when I translate the problem, you cut the problem somehow. Let's save it and then return back to this part, and then yeah, you are right. So somehow I thought this is correct, but 4 is missing. Do you follow me? You should have 4 here. So I made a mistake, right? This 4 is missing. Please add this 4 in, and then type. So solve a different problem. So initially, we tried to solve with 4, but remove 4, and then later, you may solve this problem with 4. So I somehow missed that. Thank you. Let's stop here, and if you have questions, you can approach and ask.